Hey guys, this is the 2008 Bc Frq number 3 Form A. This one actually seems pretty nice. We need to notice a couple things. The derivatives up to the fourth derivative are all increasing. It's important to know. So let's go ahead and do this. A first degree Taylor polynomial so that's going to be our function. What's the center? Center at 2. So that's the format of our first degree Taylor polynomial. We just plug in the numbers from the table. H at 2 is 80. The derivative is 128. And now we're just going to plug in 1.9. And we'll use that to approximate the actual function. So I'll put a squiggly equals. Couple of notes. This is just a tangent line approximation. So how do you know if a tangent line approximation's over or under? Well, basically it's going to be the concavity. If a function's concave down, you will notice that all the tangent lines are, wow, those are fat lines, are going to be above. It's going to be an over approximation. And similarly, if a function is concave up, you will notice the tangent lines will all be under. So we just have to check the concavity. Couple ways to do this. We are told that we can do this, I guess. Go back to my pen. One option would be, say, since h prime is increasing, therefore h double prime is positive. Well, if the second is positive, you're going to have an underestimate. You can say P1 at 1.9 is less than h of 1.9. Actually, therefore. So we have the underestimate. Or another way to look at it, let's go ahead and erase this. How else can we get the second derivative to be positive? Well, from looking at our table, our second derivative is positive on our table. And we're looking at 1.9, that's between 1 and 2. So since h double prime at 1 is positive and h double prime is increasing, therefore h double prime at 1.9 has to be positive. Then we can say, therefore, the approximation is less than the actual value. So that's part A. All right, this should go pretty quickly. Let's do part B. I don't know why the red lines aren't erasing. Oh, okay, I have to tap on it. And then, no. Wait, I think I know. Yeah. There we go. Okay, for part B, third degree centered about 2 to approximate h of 1.9. So we're going to go through the same process. The third degree Taylor polynomial centered about 2. This is the basic format. Then after this, all we do is plug in the actual numbers from the chart to get our third degree Taylor polynomial. So we're going to get 80 again, and then 128, h double prime at 2. It's going to be 488 over 3. But we also have a 2 factorial on the bottom. And then the last one is 448 over 3, like that save, huh? X minus 2 cubed over 3 factorial. And then the last step, we just plug in 1.9. So the approximation for h of 1.9 using our third degree Taylor polynomial, just plug in 1.9 into our Taylor polynomial, and we are finished. Remember, you don't have to simplify the coefficients or anything. Whoa! Did anyone notice that factorial is upside down? Oh no. Oh no. Oh no! Let's undo that. Bad things are happening. There we go. Okay, there's our answer. We are all done. We do not have to simplify that. And now we're going to go to part C. So use Lagrange error bound to show the third degree polynomial, Taylor polynomial for h about x equals 2 approximates h at 1.9 with less than 3 times 10 to the negative 4th error. All right, so in Lagrange, we're guaranteed the error. So we're going to say the actual value compared to the Taylor polynomial we just used. That difference is less than or equal to the next unused term. So it's going to be the fourth degree. The general fourth degree term, we want to maximize that term. So we're going to take the maximum value, and our C needs to be between the center point and the point being approximated. And it's the absolute value of the fourth derivative times, and it's going to be the absolute value of 1.9 minus 2, wow, I'm getting blurred here, to the 4th power, and that's all over 4 factorial. Now, we know that h to the 4th power is also increasing, and our interval is from negative 1.9 to 2. So if we look at the numbers, so since we have an increasing function, the maximum value will be at 2. So the maximum of the 4th derivative from 1.9 to 2 has to occur at 2 because it's increasing function. So I use 584 over 9. And then we have 0.1 to the 4th. And that's all over 4 factorial. And I'm hoping that's less than 3 times 10 to the negative 4. Now, if I did my work right, that should be good. This is a calculator question, so you can plug that in your calculator. I guess I could do that just to double check. 584.1 raised to the 4th divided by 9 and divided by 4 factorial. Sorry for the delay. So we get, just a side note for you all, this part on my calculator comes out to be 0.00027. And we're good. We are golden. That's 2.7 times 10 negative 4-ish. If you want more, it's 0.37. So we've done it. Your favorite problem, Taylor, or I should say Lagrange error bounds. Congratulations if you did that right. And if you did it, hopefully you learned something. That's the end of problem number 3.